Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi, everybody. So I'm going to be talking about this thing that I thought would be very, interesting and timely, which is how we managed to take a large piece of legacy software and make it run twice as fast on a quad core. Before I get into that, I thought I would just provide a little context for where this project fits in with the other research that I've done. So the initial projects that I did in my group were focused on performance things. In particular, how do we extract thread-level parallelism? In fact, that's what this talk is about today. And the other thing we worked on was how do we make better use of caches? And so I've given talks about having worked on both of these things generically, we then focus specifically on how to do it for databases. How do we redesign databases to make better use of caches? And that's something I've given talks about here at Microsoft in the past. So Shimin Chen was one of my students, and he was a Microsoft fellow and a Microsoft intern and all that stuff. Today, I'm actually working on two projects. So the first is we call log-based architectures, where the goal is to detect and fix software bugs on production systems without slowing down the application. So I gave a talk on this project the last time I was up here about a year and a half ago, and I'm hoping to come back sometime in the next couple months and give you an update on some more results that we have on this project. Finally, I'm working on this sort of far-out science fiction sounding project that I'll be happy to talk to you about after the talk if you're curious, where we want to physically render moving objects and build the holodeck. Okay, but what I'm talking about today is the sort of capstone of a project that we did at CMU that we called Stampede, and this was really Chris Callahan's PhD thesis work. This is the first time that I've given a talk that's not on something that we're actively working on this moment. So this is something we completed a couple years ago. But the reason why I'm talking about it now is I happen to have never talked about it here at Microsoft. And I think it's also very relevant today with multicore and people trying to parallelize software. So also it's very timely because people at hardware companies are making decisions right now about including the hardware support that I'll be talking about. So if people from, say, Microsoft thought that support was interesting, that might affect the world. So the starting point for this is multicore. So today we have quad cores, and the projection is that we'll have more and more cores over time. So we can't crank up clock rates anymore, but we can stamp out more and more processors on a chip. So clearly, if you're interested in increasing throughput, there are more cores to run things on, and it's good for that. But what about simply making things run faster? So one view of the world is, don't worry, everything will be fine with multicore, because from now on, everyone will write parallel software, and it'll all speed up perfectly. So that's an optimistic view. It'd be great if that was true, but I've spent 14 plus years teaching people how to write parallel software, and the empirical data suggests that it's difficult to do that, to make it both correct and fast. So hopefully people will get much better at this, but that's a challenging thing to do. We don't expect that to be fixed overnight. And there's also this issue of legacy software. So what about things that are important that have already been written that aren't parallel? Or what about pieces of things that maybe they have been parallelized, but there are important parts that haven't been parallelized yet? So that's actually what I'll discuss today. So another sort of rosy view of the world is, don't worry, multicore is fine because we'll have these fancy compilers that will automatically parallelize everything, and so it'll all speed up perfectly. So I've actually worked on projects before where we were trying to do this, and that was the original motivation of the thing I'm talking about today. It's very difficult for compilers to do that. Other than for sort of scientific programs where the dependencies are very straightforward to think about, this is very difficult. In particular, ambiguous data dependencies are a major stumbling block for the compiler to try to do this type of thing. So this motivated us at, yep, question?
So there's a don't worry that that you missed, which I often hear, which is, oh, don't worry, these chips are mainly used for web servers, and everything is inherently divided up into so many little chunks that we can keep these cores busy. Or the user's running so many processes that we're going to keep these cores busy.
Well, fortunately, there are enough of those things around already that are interesting that there will be some immediate value to having these processors. But I think that over time, it'll be nice to have more and more things taking advantage of them and not just the sort of embarrassingly parallel workloads. But fortunately, there are embarrassingly parallel workloads, so that gives us something that's ready to go on all these processors. So our motivation was, what do you do about those other things, though? What about the things that you care about that aren't embarrassingly parallel? Those things do exist. So the idea behind our Stampede project at CMU was we wanted to have through a combination of hardware and compiler support, we wanted to create this capability that you could optimistically run things in parallel without knowing for sure whether that was safe. And several other groups, like at Illinois, Stanford, Wisconsin, other places, have looked at similar ideas. And the idea is you create the threads, you hope that there aren't dependencies, but the hardware will monitor whether there really are, and if there are, things will roll back. So it's a little bit like a transaction. People have been talking a lot about transactional memory, but the difference is that with transactions, you already have concurrent threads, and you're just trying to get them to not trample each other, data structures. Here, we start off with serial execution, and we know the order in which everything should occur. So if there's any conflict between two things, you know which one is supposed to win. It's the one that's supposed to have executed earlier. But there's actually a lot of similarity in terms of the hardware to make this stuff work. So our initial motivation was the previous slide, which is we're going to automatically parallelize everything in the world, and it'll all speed up nicely. So we did use this support to parallelize the spec integer benchmarks, and we found that they did run about 20-35% faster, which is actually respectable for if you compare that with typical architectural optimizations. Usually an architectural idea is successful if you get, say, 10% improvement. So compared to that, it's not too bad, but it's not exactly the linear speed up you're hoping for. So what I'm talking about today is something different, which is rather than this fully automatic approach, we're looking at, first of all, a much larger and more interesting piece of software. We're looking at Berkeley Db, which is a database, or part of a database. And rather than doing something fully automatic, we're doing something semi-automatic. So the programmer actually is involved. There's this iterative process that I'll talk about where the system tries something, it doesn't work very well, gives feedback to the programmer, they make a decision to tweak something small, and they go back and try again. And I think that this approach is actually extremely promising, and you'll see that it actually worked quite well in this case. So this is what I want people to hear about, this sort of semi-automatic approach. So the application that we're looking at, it is Berkeley Db, so it's a database engine. Now, databases are already run in parallel. What we're trying to do here is run them in parallel in a new way, which is we want to take individual transactions and break them into parallel, and split them into parallel chunks. The way that you typically get parallelism is you get parallelism across separate transactions. We're still doing that, but we wanted even more parallelism than that, so we're breaking them up. Now, the reason why I think this is interesting beyond databases is really you can just think of this as an example of a big, complicated piece of software where the thing that we're trying to parallelize was not written with parallelism in mind. In fact, it was written under the explicit assumption that you would never try to run pieces of it in parallel within a given transaction. It is not safe to do that at all. So if you tried to actually sit down and rewrite the code so that you could exploit intra-transaction parallelism, this would take a very long time and be very painful. You'd have to understand a very large amount of the code, and it would probably take years of effort, I think, to do that. I think you'd actually really have to start over almost from scratch with a lot of fundamental structures. So, okay. But we're not going to do that. All right, so switching into this. So now we're going to dive into Berkeley DB and talk a little bit about transactions in particular. So here's my student, Chris, who did the work. I guess this is his idea of what database users look like. So we've got our cavemen here who are writing their SQL code and sending it into this database server. So here come their transactions. And then what happens is we've got this SQL server, big DBMS sitting here, and the actual data stored. And how are we going to get improved performance? Well, today what happens is separate transactions get to run in parallel on different cores. And we get throughput from that, and that's good for performance. Now, why do we want to make transactions run faster? Well, first of all, people do care about latency. So if it takes too long to run my transaction, I get annoyed. And also, if one of the transactions is grabbing a lock, that prevents other transactions that need the same lock from executing. So that actually does hurt throughput. So what can we do about transaction latency? So if you look at TPC-C, so this is a benchmark for transaction processing, the transaction within TPC-C that takes up the most time is something called new order. So you're placing a new order. And here's a pseudocode version of that transaction. So, and you're basically, you've got a basket of items, and you're going to update the stock information for all those items. So here is one query within it. We're going to do this select. And one thing that you can do, that databases do today, is try to extract parallelism within a particular query. So I can take this select and break it across multiple processors. Now this idea works really well for decision support. So if I'm launching queries that are going to take a long time, then I can get some really nice performance out of this. But unfortunately for transaction processing, these queries tend to be very short-lived. They don't run for very long, so I don't get a whole lot of performance this way. Okay, so that's not so great. What I'd prefer to do is actually get parallelism across separate queries or within one transaction. So for example, I could take different iterations of this loop and try to run those iterations in parallel. So that sounds good. But this doesn't work. This would break Berkeley DB and probably a lot of other systems because they're not written with this in mind. None of the internal structures like locks and latches and all those things are set up to work this way. So, but as you'll see in this talk, the safety net of thread level speculation makes it much easier to fix this problem. So let me talk just briefly about thread level speculation and how that works. So if you imagine some original thread, so this thing is executing in time, and when we try to run it in parallel, what we're really doing is taking something that was supposed to occur later and we're running it concurrently with this logically earlier chunk of work. And we're dereferencing pointers. So the thing that can go wrong, and we want to label all of these with some logical timestamp, and the system does that automatically. So we realize that this one is supposed to occur before this one. Okay, but sometimes bad things happen. So for example, we do a load from a particular address, and we loaded it before it was stored over here. So we saw the wrong value, and the same thing happened here. So this is bad, because that's not possible. So what happens is the hardware detects this. It notices that this bad thing happened, squashes the thread, and then restarts it. And the second time through, good things happen. So now all the data dependencies get forwarded correctly, and it works. So what we see is we use these logical timestamps that we call epochs to number the different threads. And the hardware is going to detect problems and restart things. And this is a little bit like recovering from a transaction, like I mentioned before. Yep, Ed?
So is your experience looking at these database queries that most of them do not have data dependencies between iterations? They'll have data dependencies within iteration. Data dependencies between iterations don't exist very often, which is why TLS gives you a nice benefit.
That's a really good question. And the next couple of slides are going to dive into that, because that actually is, the answer to that is, I think, is very interesting. So hold that thought for 1 second. But the idea with the mechanism the idea is hopefully, in the worst case, we run about as fast as sequential execution. Now, actually, we run a little bit slower than that because there are some overheads. And in the best case, if there are no dependencies, we get full parallelism and great speed up. But the key thing is data dependencies. So how often do these dependencies exist? Now, this is going to start addressing Ed's question here. So the motivation for this hardware support was actually spec integer type of programs. So little things where we have relatively small threads from loops. And in those cases, dependencies tend to be fairly infrequent, and the threads tend to be relatively small. So if it's painful to recover from speculation failing somewhere, it's not that big of a deal because most of the time there aren't any problems. But when we look at databases, when we look at transactions and parallelizing them, the threads are much larger. They're typically, these are maybe hundreds or maybe 1,000 or so instructions, and these are tens and maybe even hundreds of thousands of instructions here in these things. And there are many dependencies. There are typically dozens of real dynamic dependencies between these threads. So we see, in contrast to the easier case, we have lots of dependencies. So we can't, it's not okay if we only win when there are no dependencies. We'll never win. They're always there. So we have to find a way to tolerate dependencies. So I'll talk about that. So we actually learned something new about how to design the system from doing this. And we also have to have much more buffering to store these larger threads. And in the second part of the talk, I'll discuss how we address those things. We also have concurrent transactions that we're speculatively parallelizing, so that has to work, and there's a nice way to make that work too. Okay, so there are a lot of dependencies, but there's some good news here, which is the hardware is already tracking dependencies. It has to do that to realize when it needs to restart things. And the information that it's capturing happens to be exactly what you'd like to know if you were going to fix a problem. So it knows, that didn't work because of this particular load and store pair. So the idea is when you see a problem, you can actually give feedback to the user and say, that's the immediate problem right there. This speculation failed because of this. And if you can fix that, then you'll get to see the next one, and then the next one, and the next one. So you can, if you choose to, and this is what we did in this study, you can incrementally fix dependence by dependence. And you don't have to make them all go away. It's just each time you do it, you might see slightly better performance. So that's the idea. Okay, now there's one non-intuitive thing that can happen, which is sometimes eliminating a dependence can make things worse. So in this case, we have, on the left, we have this original case where there's a dependence between P and Q, and P triggers a problem first. So if we eliminate the problem with P, and now Q triggers the restart, we actually restart later. It takes us longer to realize that there's a problem, and we actually have worse performance. So that's annoying. So one of the things that we did is we fixed this. And really the fundamental problem is having to get an all or nothing, having all or nothing as the mode of execution isn't so nice. So to fix that, one of the new things that we modified in the system is we essentially added an extremely super lightweight checkpointing mechanism where we can keep these different checkpoints such that if something goes wrong, we only have to back up to the most recent checkpoint. We don't have to go all the way back to the beginning of a thread. And that was really important for making any of this work. I'll show you numbers on that later. So now we have a more robust system design that will work much better because of this. Okay, so this was critical to getting these. The relative speed up from having this was really important. We were, with this support, we could get speed ups of around 1.9 to 2.9. Okay, so yeah, sure. Mm-hmm.
So do you synchronize the frequent checkpoints across threads? Because you can certainly have a case where the thread on the left runs behind and ends up conflicting with something in the previous subthread. I mean, I can imagine cases where you have to roll back more than one.
Oh, multiple of these things?
Yeah, or do you guarantee that doesn't happen?
I do have some backup slides on that, but basically we do have this issue where you have a whole chain of things that you have to cancel. I don't know if that's what you're asking about. So we do have a way to We can selectively roll back to the most recent checkpoint in each of the threads if we have a chain of things that we have to cancel. I'm not sure
Do
if
you
that's
ever roll back more than one checkpoint in one thread?
So what we do is we're lazy about rolling back threads. So we don't roll them back aggressively. So we will only roll back once, if at all. We don't roll back multiple times, because you could imagine discovering more and more dependencies and eventually rolling the whole thing back. So we didn't do it aggressively. We did it lazily. It's only when we would commit a thread that we only triggered it at commit time. So this picture looks a little funny. This isn't actually quite accurate. It doesn't happen at the moment that this occurs. It actually happens a little later.
Right, no, I assumed that. I was just wondering if you could, could I have a violation that would roll me back 3 of the checkpoints on the right-hand side?
Oh, I see. Yes.
Yes, okay.
Yes.
Okay. So you have to be able to roll back to any number of them?
Yes.
Yeah, okay, great.
We recognize, so in this picture, what it's trying to show is that you actually, it's hard to see, but we actually rolled back to this checkpoint.
Oh, I see.
This load was above this checkpoint. It's right here, and here's the checkpoint. So we actually skipped this one and went back to this one. So we know which checkpoint is the most recent one ahead of you. Okay. Yeah.
So checkpoints are taken locally and not globally across all the cores?
Yes. Yeah. And I'll show you later, but it's a trivial mechanism for checkpointing that works only because we're already supporting thread level speculation. But we just bump a counter somewhere. That's all we do. Okay, so to make all of this work, there are different layers here. There are transactions running on top of a DBMS, running on top of a system. There's an operating system in here too, of course, but it's an operating systems company. I forgot to mention the operating system. Okay, I'll be shown to the door now. Okay, so in particular, what we're running is TPCC as our transactions on top of Berkeley Db, because we had the code to it, on top of a simulated machine. We'd like to have run it on a real machine, but the hardware support didn't exist. So now this involves different people changing what they're doing a little bit. So the transaction programmer, we don't want them to change anything that they're doing. If they choose to, they can explicitly indicate where they want to break their transactions into different threads. In our experiments, we simply took every loop in a transaction and ran loop iterations in parallel, and they didn't need to do anything to do that. So there are a lot of people who do this, so we don't want to put any of the burden on them. There's a lot more interesting stuff that happens for database developers. So they do have to change things, and that's actually most of what the talk is about, is how we fix that. Now, that was the part that took a month. So there's more work to do here than here, but this still isn't a lot of work. And then there is some work for hardware people to do, which is to put this into the hardware, and that's been sort of very well studied, and right now it's just a value proposition argument that people are actively debating right now.
Would you say that TLS hardware research is mostly done, or are there new capabilities that you think might pop out? I realize it's hard to predict the future, but you've worked in the area a long time, so.
I don't think anyone's really actively pushing on it right now, or I think it's mostly cooled down at the moment, but it could become interesting again. So for the moment it's paused, I think.
But in terms of do you see significant unsolved problems remaining from the TLS implementation side?
No.
Or it's basically, most of the problems are solved, and if you can just find the right set of stuff in the higher layers, then it'll take off.
Yeah, the reason why it's not in today's hardware is not because designers don't think that there's some major problem that would prevent them from implementing it. It's just because they haven't been convinced yet that people want it. But they know how to design it. I've seen many different designs that all seem reasonable, so people aren't worried about whether it'll work, just whether they should bother to do it. So I think once it really exists in hardware, it'll probably make the research interesting again, potentially, because there'll be much more interesting software built around it, and then that might make life interesting again. Okay, so if you're, say, looking at the world from a database perspective, the thing that's new and interesting is we have a way to extract parallelism within a transaction without actually changing the transactions, with only small changes to the database management system, We don't have to change anything about locking. We didn't introduce any bugs, and we got nice performance. We made transactions run twice as fast on 4 cores. OK, so here's an outline of the rest of the talk. So there are really 2 parts to this. The first part, I'm going to talk about how the database changed, or how the database layers changed to take advantage of thread-level speculation. And then I'll briefly talk a bit about the hardware support. So these are the new things we learned by doing this as opposed to spec benchmarks. Oh, but the first part is the transaction programmer. So we have to divide the transactions into separate threads. So looking at new order again, it has this loop. And if you look at this loop, it takes up, so new order is the most important transaction. And this loop takes up about 80% of the time in the transaction. So this is the hot spot. And if we can make this run in parallel, that's a good thing to do. And in fact, if you focus on the code, it looks like this is almost embarrassingly parallel. Well, almost, not quite. So it's possible that different iterations will depend on each other if the same item appears multiple times as separate entries in the list. That's possible. For the benchmark, it turns out that the definition, given the way we configured it, is that this will happen once every 100,000 times. So this looks like a great opportunity for thread-level speculation because we'll only fail once every 100,000 times. So at this level, it looks very good. So all that you need to do is decide that you want to run this loop in parallel, and the programmer can either explicitly annotate that or not, or you could just have the system decide to do that. So there's not much work for the transaction programmer to do, and that's good. OK, the next part is, what about the database developers? How do we remove problems from the database management system? So what we'll see is, in fact, just simply doing this didn't work very well at all. There were a lot of problems, and they didn't occur at the SQL level. They occurred inside of the database itself. OK, so I had this picture before where I showed that what happens is we try to run things in parallel, and they don't run very well in parallel because there really are a lot of dependencies. So what we're going to do is use the hardware support gives us profiling feedback where we can tell exactly what the pieces of our code were that caused this most critical dependence. Then we can do, hopefully, a small, simple thing to fix it. We get a little bit better performance and a little bit better, and so on. So that's the idea. Yes?
At the beginning of the talk, you sort of mentioned that transactional memory, you still have a version of your code that is, in a way, explicitly parallelized by the programmer, whereas here, you're starting with legacy code. But nevertheless, at the end of the day, it seems like you are going to make modifications to existing applications. So it seems like a natural comparison would be to take this database and try to parallelize it using transactional software or hardware implementations of transactional memory.
That's a good question. So I think the amount of effort to take this and OK. So I think there's a very big difference in terms of the amount of effort involved. Because transactional memory, the starting point is that you already have a concurrent program. And that it's mostly, it's correct. And you're just trying to take a critical section and get better performance out of it. That's an important thing to do. But you're starting with something that's already concurrent. In this case, we're starting with something that's sequential. And we never get to the point where we really have a properly threaded program. Instead, we're just fixing we're relaxing some aspect of the program and making it a little more parallel, but we're not bothering to fix all the other things in the thread. So if I didn't do the actual study of trying to rewrite Berkeley DB where we would rewrite the threads, but as I said before, I think that involves almost starting from scratch in terms of writing the code. It's a really fundamental assumption throughout the software that there are never multiple threads within one transaction. And I think that would be measured in years of effort, not a month of effort to do that. So transactional memory is a good thing, but it's for a different purpose than this. OK, so what I'm going to do now is talk about one concrete example of something a case where we found a problem and fixed it, just to illustrate the types of things we found here. So one important part of the database is the buffer pool manager. So this is a little bit like the virtual memory system of the database. When we access data, so the buffer pool is this section of physical memory. If you access something that's on disk, you say get page in Berkeley DB, and it grabs something off the disk, puts it into memory, and then to make sure that it doesn't get displaced until you're finished, it bumps a reference counter. So we realize somebody's actively using this. Then you get to access it, and when you're finished, to release it, you say put page. That decrements the reference count, and now that page can be reclaimed by the buffer pool manager if you need more physical memory. OK, so what happens when we try to run the code in parallel and looking at these two primitives? So let's say that so we're originally going to run this thread, and then this thread is supposed to run after it in the original program, and we're optimistically running them concurrently. And they both want to access page 5. So they do a get page, they do some work, and then they do a put page. It turns out that speculation will always fail here. And the reason is because of this reference counter. So when we decrement the reference count here, that's going to cause the reference count value that we read here to look like it was wrong, because it just changed and we read an older value. So it'll squash speculation, and this will never succeed. But if you stop and think about it for a minute, that's not really, that's a little, although that is strictly what the sequential execution would have done, we don't really need it to behave that way. We want buffer pool management to work, but we don't care about this artifact here. So I don't really care, in particular, I don't care which of these pages which of these threads grabbed the page first. I just want to make sure that they have it pinned in memory the right way when they access it. So what we can do in this case to fix this is we can temporarily turn off the speculation tracking mechanism. We can say, we're about to do something, and we don't want you to treat this as something that's a problem. So we're going to go ahead and change the reference count. In order for this to be OK, we have to realize that it's possible that this thread may get squashed for another reason. And if that happens, we have to have a way to undo the side effect that we just did. So fortunately, that's easy to do in this case. To undo a get page, all we have to do is decrement the counter, and everything will be fine. So what we do is we escape speculation, we do the operation, we store an undo function, and then we turn speculation back on again. Yep?
You said decrement the counter. Do you mean call put page, or actually decrement the counter that get page increments?
Yeah, I meant call put page. OK, so to show you the actual code, here's what we did. So we implemented this, again, by hand. This isn't automatic. Chris decided that this was the thing to do. So we put a wrapper function around getPage. In the middle of it, it calls getPage with this ID that we pass in. In addition, as I mentioned, we turn off speculation. So we have an instruction to our hardware that says, turn off speculation, don't track it. And then we turn it back on here. We also do some extra checking of the arguments to make sure that they're OK, because when you're running speculatively, you may get a bad ID, and we want to make sure we don't do anything bad inside this routine. So we do some extra checking here. Also, we don't know how to do multiple get pages concurrently without thread level speculation turned on, so we also add a mutex to make sure that there's only one active call to get page at a time. And then finally, we say that the way that you undo this is you need to call put page in order to undo get page. And this works because the effects here are isolated. It's not going to cause a cascading chain of aborts if we do this. We have a way to undo all of our side effects. And this can be used for other things like memory cursor management or malloc, for example. So, yep.
Do you run into problems if the operating system sort of deschedules one of the threads in this speculative team at any given point in time?
Yes. So we don't want that to, the problem is that nothing crashes and burns. What happens is speculation will fail. That's actually really the only thing that goes wrong, I think. We want things to be gang scheduled if you want it to work. In general, if you have a parallel application, you swap out one of the threads, unpleasant things can happen. if you're holding a lock.
In a way, you'll still be able to detect conflicts, even if one of your newer threads is not scheduled at the time the conflict manifests itself?
Yes. Well, okay, what happens is we have a limited ability to detect conflicts, but if things ever get knocked out of the cache, then we just say there's conflicts. So our default is we squash everything. So we can always fall back to that. That's the reason why it still works if the operating system reclaims something. It's not fast anymore, but it's functional. Okay, so we know how to fix the problem with getPage, which we just described. Now what about putPage? So here we are decrementing the reference count. So can we play the same trick here? We can't, because getPage is not a proper way to undo. You can't undo putPage with getPage. It may end up going somewhere else, and this could cause very different behavior. So instead what we do is we just postpone doing the putPage until the thread receives this token that says you are no longer speculative because everyone ahead of you has already committed. And it's definitely safe to do that. Now the downside is we're actually increasing the lifetime in which this is pinned in memory. But that's a trade-off that seemed okay because we're only increasing it like by a couple of thousand instructions maybe, or tens of thousands of instructions, and memory is large. So we're not too worried about that in this case. So if we do these two things, we can now actually run code with get pages and put pages in parallel, and that won't cause speculation to fail. So this is one example of the type of thing that we are doing. Okay, so in general, delaying something until the end of the epoch when you're not speculative is another trick. So Chris went through, as I said, in the title of the talk, he spent a month's worth of effort going through this process of finding something, fixing something, finding the next thing, and fixing it. And the other thing I forgot to mention is that Chris had never seen Berkeley DB before he started doing this, and he doesn't know much about databases. He's a systems guy, not a database guy. He never took a database course or anything like that. So to him, this was just a big, giant piece of software that he didn't understand. But of all the fixes that he made, these basically fell into three buckets. We saw the two things that we just saw, escaping speculation, which you saw for getPage, delaying an operation, which we saw for putPage. And then the other bucket was there were several cases where there was a central structure, and the solution was simply to distribute it, have a parallel version of it across the different cores. For things like, say, gathering statistics, you could gather local statistics and then just add them together later rather than having one counter. That's one simple example here. So these are the things that he did. OK, so now I'm going to show you some performance results here. So we simulated a quad-core processor. It was a out-of-order superscalar. Here's the memory hierarchy that we were modeling. We were running TPC-C in core. We weren't worried about disk accesses. So we're also measuring the latency of a transaction, not its throughput. OK, so here are our results. So first I'm showing you the original unmodified version of the application running on one core on a quad core. So that means 3 of the cores are doing nothing because it's a sequential piece of software. At least one transaction is. So the way this is color-coded is that black means that there's a CPU that's doing nothing. So 3 of the processors, this is renormalized to execution time, are sitting idle. And of the one processor that's busy, the blue part is the time when it's doing useful work, and the green part is the time when it's stalled for cache misses. OK, so now we've got this wonderful thread-level speculation mechanism that we spent years developing, and we turned it on and parallelized this embarrassingly parallel SQL loop, and we got a slowdown. So things were worse than they were originally by a little bit, about 8 or so %. And this is without any of the optimizations that I just mentioned. And the reason is that the speculation is always failing. So the red part is time when you've done work that you have to throw away because it wasn't useful. It's a little bit worse in part because the cache miss time actually went up a little bit, because previously all of the data was on one core's cache, and now we've spread it across all the cores, so sometimes our cache misses are more expensive because we have to go get data from other cores' caches. So we lose a bit here. So then Chris started going through this process of iteratively fixing things. So first he fixed a problem with the latches, and things actually got even a little bit worse. And he fixed a problem with locks, and we're still not speeding up. And then he fixed a problem with malloc and free, and things are still not good. And then he fixed a problem with the buffer pool, and suddenly we saw a nice jump in performance. So more than a quarter of the latency disappeared. Now, you might wonder, well, why did he bother to do the first three things? Why didn't he just jump to that fourth step? And the answer is you actually had to do all of them. They were, 4 problems lurking right underneath each other. And when you eliminated all of them, we saw this improvement. And then he kept going, did something with the cursors, error checking, fixed some false sharing, fixed something with B trees and logging. And we eventually got down to almost nearly a twofold speed up here. So, yep.
Are all of the techniques?
They keep adding on. I don't know if that's what you're asking. But
I assume that. But are all of them necessary to get close to that final performance? I know you said that they were all lurking, but are every single one of them important?
Yes. So the way we get the feedback is that the hardware always tells us the most critical one.
Yeah.
So if we didn't fix that one, it wouldn't matter if we fixed anything else underneath. Well, it might matter if we eventually fix the critical one.
Right.
But until you fix the critical one, you won't see any improvement.
No, I understand. But
Yeah.
if you take that endpoint that has everything.
Oh, well, these last two didn't really improve any upon this one, if that's what you're asking. We didn't really need to go all the way out to this point. Like once we got to that point, kind of leveled up.
Starting from the false sharing point,
Mm-hmm.
could you, for example, not do the cursor queue optimization and do fine?
No.
Okay, so
Well, I mean, you wouldn't do any better than that. I mean, if you wanted to stop here, fixing these things without fixing that would not improve anything beyond this. They're sort of strictly ordered in terms of being the more critical dependencies. And if you don't fix them, you don't get to move to improve the performance. Yeah.
So the y-axis in this plot is measuring latency once my query has started executing on that chip.
Yeah.
So I have a comment about this, but maybe unfair. Nevertheless, I'd like to ask.
Right. Unfair is fine. Got it. I might give you an unfair answer.
At the end of the day, the user most likely ends up sort of worrying about the end-to-end latency of the entire operation, and part of that has to do with the queuing delay involved in the server. And now that you are parallelizing your individual transactions, there's a good chance that the queuing delay itself, the waiting time that leads up to my being dispatched to this multicore chip might get higher, and as a result, under a reasonable load, this may end up not making a big difference, or it may even make things worse.
Yeah, so the one big caveat I think, for interpreting this work is there actually are legitimate arguments you can make about why you may not like this feature all the time, certainly in a real database system. If you did have enough transactions to keep the entire system busy, there's certainly no reason to turn this on. You would only want to turn this on if you actually had idle resources and you're willing to pay the power cost of turning them on. So you have to keep that in mind. You don't want to saturate the system and you don't want to make non-speculative work slower by doing this, or it will hurt throughput and potentially even latency. But the other way that I like to look at it is just pretend that this isn't a database system. Just take a transaction and say, well, this is just, ignore what it's doing. This is a pretty complicated piece of software, and we managed to make it run a lot faster.
How lightly or heavily loaded are typical systems that run this Berkeley Db application?
It's very bursty. Yeah, that's my impression. So sometimes they are saturated, but most of the time they're not saturated. It's very bursty. So you'd want to monitor how the bursts and not turn this off during a burst, probably. It's easy to turn this off. You can turn it off in like one instruction. So
how much does your programmer need to worry, about the underlying microarchitecture versus just the code? So for example, false sharing is an example where there's no hardware details, and then B, about the specifics of the speculative threading protocol.
Okay, well, yeah, file sharing was really the only one we needed to know anything about the memory system. And in this case. So, other than that, there weren't any other like system parameters that you would need to know, other than that, like your ability to buffer threads. You would want to realize that you shouldn't make threads that are way larger than your system's ability to buffer things. But we never actually thought about it. We just tried to design something. I mean, we just used the second, well, I'll talk later about the hardware support for this and why we can buffer enough state. But yeah, when Chris did this, he wasn't thinking at all about any system parameters. He just realized that, oh, that's not parallel code. I could make that parallel code by doing this little thing. And the key thing that I probably didn't emphasize is the reason why this works so well and you can do it so quickly is that you don't have to actually go off and understand all of the code when you make one of these changes. You can just zoom in on this specific thing you're working on, change it, and you can still have lots of other problems going on. In fact, even as he's doing this, there are still dozens of dependencies sitting underneath this that are causing things to. So we never really get full parallelism. We get partial parallelism. Things are somewhat overlapped, and that's why we get a speedup of 2 as opposed to 4 on 4 cores. Maybe possible to push it further, but we didn't work on that. Okay, so at this point, we actually can't improve this much more because the only part of execution time that gets better with better speculation is this violation time, and that's already fairly small. The reason why we aren't running faster is that the number of iterations in this loop isn't very large. So we just don't have enough parallel work to keep all the cores busy in many cases. So that's really the bottleneck. We tried an artificial experiment where we just increased the number of iterations artificially, and we got much better speed up. But that's what you would expect. And again, the important part is it took Chris 30 days of effort, and he changed less than 1,200 lines of code out of 200,000, and he didn't understand the application and didn't really know. I mean, I don't want to make Chris sound like he's not a bright guy or something. He's a very bright guy. But you don't need to be an expert on this to get this kind of improvement. So we looked at the other, new order is one of the 5 transactions in TPCC. We did the same process to the other 4. 2 of them sped up very nicely, even more than new order. So delivery is running, we've eliminated 2/3 of the execution time here, and stock levels running more than twice as fast. The other 2 cases did not improve. And in these cases, there weren't loops. And there were a lot of dependencies. We couldn't find any obvious way to break them into smaller chunks. So this doesn't always work, but it worked well in these 3 cases. Okay, so for a database type audience, the conclusions from this are that we found this new form of parallelism. We can now break up transactions into different chunks. We did have to change the database management system, but it didn't take very much effort to do that. And we think this could be applied to more than transactions, not only within databases, but other types of software. Okay, so that's the main part of the talk. I've got another, little part.
Did you look at energy efficiency or power?
No. Okay, so I mean, you just have to decide what your preferences were. If you are incredibly stingy about energy, then don't speculate. But then relative to your preference for latency, I mean, improving performance. So there's a trade-off there, and you always have to decide how much you care about one thing versus the other thing. So this is a way to make it run faster. But without this, it's not obvious, to me at least, how you would make transactions run faster, because they're not concurrent, and clock rates aren't getting any faster. So, yep.
So you changed the code to improve the performance on the speculative case.
Right.
But when you turn speculation off, how much do you pay for these extra constructs then? So if you really want to, if you have a peak, for example, and you don't want to have speculation running.
Let's see. So, well, you can figure that out actually by just looking at the height of the blue bar. This is the software overhead shows up in this blue section. It's actually increasing a little bit, but it's only a couple %. So you're not paying very much. So that's basic answer. Yeah.
Was this a single client then? That's you're parallelising with single clients.
Yes.
Did Chris look at, as you increase the number of clients, because TPC has lots of sleep times, as you increase the number of clients, what the sweet spot was where you could still be speculating and improving performance within transactions for multiple clients, and where you kind of hit the wall?
We didn't look at that. That would be interesting to look at, but we didn't do that. So, yeah. That's a good. We did not do that. No. I don't. Yeah. So I don't know what the answer would be. I believe that the things that we did here are all. The nice thing is they're all generally useful, I think. So, after what I didn't make this clear, but what Chris did is he started with new order and he made these improvements, and then he simply ran these cases without changing the database further, database management system. So the fixes for new order are also very useful for these two cases. There weren't any other bottlenecks he had to fix. So I don't know TPCH how it would stress the database management system, but there's a decent chance that the improvements here would be useful for it. I mean, they have much longer running queries. So in a sense, part of the reason why we didn't do it is because the intra-query parallelism works so well generally that we didn't think it was as interesting, but there's no reason not to try it. So that would be another experiment to do. Okay. So the second part of the talk, I'll just go through this quickly, but this is about how what we learned about changing the underlying design of the system to make this work. So I know that the majority of you aren't architects, but you might find this a little bit interesting, perhaps. So, okay, so we have to buffer large speculative threads, and we have to deal with subthreads. So those are the main two things. So when we were parallelizing spec_int, our threads were just typically tens to maybe hundreds, maybe thousands or so instructions long. We're just parallelizing loops in C code. So those typically aren't, individual iterations typically aren't that big. But here, our thread sizes, even though we're parallelizing a loop, again, it's a loop in SQL. And beneath that is a database management system engine that's invoking lots and lots of other code. So that turns into tens of thousands of instructions. In delivery, it was almost 500,000 instructions. And this is the number of dynamic data dependencies on average between those threads. So these are 75 or tens of dependencies. So we start off with 75, and he fixed about a dozen of them. So there are still about 60 or so dependencies still there that he didn't fix, but they just happen to be less critical, and we could get some performance improvement. So one of the challenges is we have to buffer larger threads. And, well, so there's some related work here. The big difference is in our original design, we buffered everything in the first level caches, and now we realize we have to start buffering it deeper in the memory hierarchy. We had to buffer in the second level caches. This involved adding another bit to our first level cache to keep track of some extra state, and adding a few bits to the tags of our second level caches. Also, when there are collisions, an interesting thing that happens is when you're physically sharing the cache and different threads are writing to different copies of things, you end up with different versions of something. So what we did is we would actually allow replication within a set associative cache. So that was another change. And we added a small victim cache just in case we had some pathologically bad cache mapping. So those are the things we did to buffer larger threads. And that worked well. And then we also had to support subthreads. So the only trick for supporting subthreads is we already have, external to the cache, we have these epoch numbers. These are logical timestamps. They sit on the side because there are only a handful of them that are active at a time for the whole cache. Yes, Doug?
By subthreads, do you mean those incremental checkpoints?
Yes.
Okay.
Yeah. This is how we implemented incremental checkpointing. All we had to do was add support for some more virtual timestamps. Because the trick is you just bump the timestamp number. That's all you have to do. That takes no time, basically. Just adds a few more bits to the tags. Another question that we thought might be something we thought might be an interesting research question was, where do we take the checkpoints? So our intuition was the optimal answer would be that you would take let's say that this was what our code looked like, and we're going to have a dependence violation here, the optimal thing would be to take a checkpoint just before a very risky load, one that's likely to fail. So we thought maybe we need to build some predictor to predict which are the risky loads and take the checkpoint just before them. And we were excited to write a paper on this brilliant idea. But then we discovered that actually just doing something very simple-minded works quite well. If you just take a checkpoint every 5,000 instructions, it works really well, just as well as this. OK, so here are some results here. So going back to these are all the different things, plus this artificial version of new order where we increase the number of iterations by a factor of 10. Now, this is not the number I showed you before. This is what the world would look like if we did not have our checkpointing support. So remember, new order was running twice as fast before, and now it's running faster, but not nearly as fast. Delivery was running 3 times faster, and now it's only running a little bit faster. This delivery outer was running 3 times faster over here. These are 2 different versions of that. So subthreads are important. And if we had no dependence violations, if this was perfect, we would only get the bars on the right. So the checkpointing allowed us to cover much of the distance between the baseline case and the perfect case. So there's not a huge amount of room for further improvement. OK, so that's important. And subthreads didn't actually affect the cache performance, so not that we would expect it to affect it very much.
So Todd, let me ask you about that. So if you have a violation which ends up rolling back a speculative thread to a large number of what you call subthreads or checkpoints, you would expect to see a large performance gap between that and no dependence violations. And so what you're saying here is that
that shows up as this red. The red part in the middle bar is that time.
Yeah. So what's that saying is that with this technique, almost all of the time, you only roll back a very small number of subthreads. And so so this idea we discussed today of doing selective replay and only replaying the stuff that has been changed in terms of data wouldn't really be all that useful because there's not very much more to get.
Yes, that's right. Yeah, the difference between the height of the red bars is the amount we've gotten. Actually, in some cases, it didn't help very much. And these cases are never very good on the right. But in these cases, there's not much to get. In these cases, we've gotten much of what there is to get. So, yes.
How many in-flight checkpoints do you support?
I have to remember. I have to look it up. Something like 4 or 8. Just affects, you just multiply that number by 2, and that's the number of bits you have in the cache tag. That's the cost of it.
And your architectural register file is also checkpointed?
No. Let's see. Let's see. How did we do that? I forget the answer to that. I'll have to look that up after the talk. I know that we did that properly. I don't remember the answer to that. I remember discussing that, and I forget what the answer is. I'll look it up at the end of the talk, but I don't remember off the top of my head how we did that. I remember how we did it generally, but I know we didn't do it that way here. Okay, so I said we had a victim cache, and the question here is how large would the victim cache need to be with different amounts of associativity in the second level cache to capture everything that ever gets evicted. This is a 1 megabyte L2 cache. And so if you have just a 4-way set associative cache, you need dozens of entries here. If it's 8 or 16-way, then you don't need very many entries. So it can be relatively small and work. This graph is just showing the size of the subthreads with a fixed size, starting from 250 dynamic instructions going out to 25,000. And the sweet spot happens to be at around 5,000 for some reason. So if you make this too small, the trade-off is you end up using up all of your checkpoints early on in the thread, and then you run for a long time and you can't checkpoint anymore. If you make them too large, then you have to go back further to get to a checkpoint. So given how, given just the particular sizes of our threads and where the dependencies were occurring, this is where it was happening. You can easily imagine changing this dynamically. This is just something in the hardware that it decides how often to do this. So this could be dynamically adjusted.
Did you see, were all of your... This is a case where reasoning about the microarchitecture and the size of the L2 would be something that the programmer really had to do if you weren't going to do some sort of automatic adaptation of the subthread size. Or in other words, turning that around, if I supported a certain subthread size in hardware, the programmer would need to reason about that in terms of choosing the size of the speculative threads to get best performance.
Yeah, what I think would work well, and we didn't bother to do this, is if the hardware just tracked, maybe after the first iteration, the dynamic size of each thread, and just divided that evenly between the number of checkpoints that you have. I think that would work well, probably pretty well. And it turned out that with 5,000 instructions per checkpoint, and I think we had maybe 8 checkpoints, that was enough instructions that you got 40,000 into the thread, and that was, you gained enough with that everything was good.
Great.
One question.
Did you think about recycling checkpoints, kind of, so that you run out of checkpoints and then you throw away the first one and stack it on the end?
I'd have to go back and think about that. I think there may have been a reason why that wouldn't have worked, why that would have been painful to implement, but it seems like a good idea. I mean, if other than being some detail in our design why that would be hard to do, it would make a lot of sense to just sort of exponentially back off the checkpoints and just keep more of them more recently and fewer of them as you get back in the past. So that's probably another good improvement on this. But it was already working well enough that, these are a number of subthreads. So, here we go, 2, 4, and 8 subthreads. So we found that it was working well enough that, it seemed like there wasn't that much to gain by being fancier than we were being. So, okay, so from, my last 2 slides here. So for an architecture audience, what we learned are that the lightweight checkpoints or subthreads are important to get speed up in cases where there are a lot of dependencies between the threads. The fact that we get this feedback about the critical dependence is important because that allows the programmer to iteratively fix things. Now, the reason why I mention that is it's possible to build TLS and not make this visible to software. And this is something that we would want hardware people to make visible to software, because if you don't do that, you're losing a big opportunity to improve your code. In fact, I might even argue that even if TLS didn't functionally work, if you simply profiled this and made that visible to the software, to the programmer, that would be very interesting information. It would tell you just dynamically what is going wrong if I tried to run this in parallel. We found a way to deal with large threads, and this is a pretty simple set of extensions to existing design. So, final slide. So I think we got a fairly compelling amount of speed up on a large piece of software and with a very small amount of effort. And basically what we need are subthreads and this feedback that I just mentioned. So there's hope for dusty deck codes on multicore without having to invest years of time to go back and rewrite something from scratch. So if you like this idea, you might want to mention it to your friends at Intel or AMD. Hint, hint. Yes. I'd be happy to.
Don't you have ties into Intel?
I consult for Intel, so I'd be happy to introduce you to the right people. Yes?
So in a multi-circuit system, would you be able to create a speculative team of threads that span more than one chip using this technique?
Yeah, actually, we had a paper in ISCA several years ago showing exactly that. So we designed our support so that the chip boundaries didn't mean anything. So it just worked on top of coherence, and coherence can be implemented recursively, and it'll just work on any scale of system. Now, the only thing that limits that being interesting is how much speed up you get. So there are cases where you can get interesting speed up across multiple chips, where it's speculating across the whole thing. But
and do you have to do anything special with in-flight messages when you're taking your checkpoints? Although if you're checking
No.
local problem.
You just need to atomically, when you, there's a point, there's a logical timestamp. When a thread is executing, it has a logical timestamp. And the trick that we're doing is we're just bumping its logical timestamp. So we give it a range of timestamps that are contiguous. And we say, OK, now you're the first one, the second one, the next one. All you need to do is make sure that you atomically change that with respect to any cache actions. So the messages can still be coming in. You need to just hold them off for a minute while you change the count and then let it proceed. And then everything should be OK. Great. Any other questions? Oh, one more.
You did this in using simulation.
Yes.
And now it's some back already. So you didn't have plans to implement it in hardware or FPGAs or something. But do you think that the situation might change when you implement it in real hardware? Mm-hmm. Like, I don't know, adding bits to the cache might be a problem in hardware because size increases, latency increases, mm-hmm. and that it might look like a good idea in software mm-hmm. simulation where it's mm-hmm. cheap, mm-hmm. but in hardware maybe not cheap.
Yeah. So I don't believe I don't believe the absolute performance of our simulator, but I actually wrote a lot of the initial part of the simulator, and we tried to design everything so that whenever we were cutting corners on something, that we didn't think it would change any of the relative performance gains of anything. That's why I always present normalized execution time, because I think the ballpark speed up improvement is, I do believe that, plus or minus 5% or whatever, maybe. So I wouldn't expect it to suddenly be the case that this was slowing down a lot rather than speeding up a lot. In terms of the first going from the bar where we slow down a little bit in our initial, whoops, that's not the one I want, it's back here. So, in terms of how much is this slow down, I don't know exactly. It could very well be worse than that because we didn't model the extra latency to the primary cache because we had more bits in it or something like that. So that's something. There are things that we didn't model. Great.
Okay, well, if no more questions, let's thank our speaker again.
Great, thanks.